Okay, so air acoustics experiments, as we will discuss here, should give us the knowledge to see which measurement technology is mainly used. Yeah, there are a lot of different ideas clearly in research, but also in industry to investigate by experiments air acoustic phenomena. But we will focus on the main important one. And in this sense, we still have our motivation, let's say, as shown here, the ventilator. And in this case, it is clearly an example where measurements make sense. We can position different microphones, for example, at some distance of the ventilator. We can put pressure sensors both on the stationary as well as rotating part of the ventilator. However, clearly what we have to take into account is that we are not able to resolve the flow field or the acoustic field as accurate in space and time as we can do it with numerical simulation. However, you always measure on the real system, and we know when we do simulations, it is always an abstraction, it is a model of the real part at hand. Okay, so measurement technologies now, I think the most important thing is standing here. In old times, let's say 20 years ago or something, we were just speaking about wind tunnels. Now the important part since about 20 years, I would say, you call them air acoustic wind tunnels because they have found out that they get a lot of knowledge also by acoustic measurements. When you do acoustic or measure the acoustic field, you should be in an environment where you don't have too much reflections. Ideally, it would be in a room where you have totally absorbing walls. However, it's clear in a wind tunnel, at least on the floor, you cannot put there the absorbing material. At the floor, you have, for example, the car or an airplane, even a train. And so the absorption material is mainly put on the side walls and sometimes on the ceiling. And so you get quite nice properties there, and you can position at different parts your sensors, especially microphones, in order to get some resolution of the acoustic field. On the other hand, clearly, besides single microphones, we have here so-called microphone arrays. There you will also see when you collect the acoustic field by a lot of microphones, there are special signal processing algorithms, how you can compute back where are the sources. And you will also do some tasks within the exercises there. That's still a very interesting topic, which is for high frequency nicely solved, I would say. However, for low frequency, where you have large wavelengths, the microphone arrays are not really performing as we would like. So the results, as we call it then, of the source maps are not really highly resolved, and it will not help you so much. Important quantity beside microphones are clearly intensity sound probes. Intensity sound probes are simply, the standard is that you have two microphones at a certain distance. So you have here microphone 1, you have microphone 2, and you have here a certain distance. And you compute then in the direction of the connection of the two microphones, you can compute one component of the particle velocity, let's say, and in addition, by averaging the measured pressure, you can compute the pressure and therefore the intensity. We know the acoustic intensity is the acoustic pressure via the acoustic particle velocity, and the main relation we have between pressure and particle velocity is the mean density time derivative of the acoustic particle velocity is equal to minus the gradient of the acoustic pressure. So you see a possibility is to compute or to measure the gradient of the acoustic pressure, and well, that you can do and approximate the gradient, so each component of the gradient by a finite difference approach, and then you need for each direction 2 microphones. So the standard intensity probe just has 2 sensors, and you have to turn this probe, intensity probe, by hand, or you have any automatically equipment with motors. And we have, so this is the standard approach, which is very robust and used in all the different environments. Another approach is that you have a real sensor which is able to measure directly the acoustic particle velocity VA, and that can be done by some microelectromechanical systems. So one of the main probes on the market is given by Microflone. So I just write here. So Microflone, you can Google and find this company. So they have a MEMS sensor for measuring VA. So all 3 components directly. Yeah, and if we go towards the fluid dynamic part, then clearly it's quite nice. You can visualize somehow flow structures by LDA, so it's laser Doppler anemometry. And however, there also you are restricted towards the resolution in time and space. But anyway, with these laser devices, you can nicely visualize flow structures. And a standard approach, but nicely helping us, especially in aeroacoustics, is to measure the pressure directly at walls and get their idea about the amplitudes and phase distribution on different positions towards the pressure. However, we have to be we have to have it in mind that pressure sensors, which are also clearly the sensors we are measuring the acoustic pressures, they are also pressure sensors. You are locating these acoustic pressure sensors, the microphones, in the far field. So we will really measure there the acoustic sound pressure. On the other hand, when we position pressure sensors directly within the flow structure at the walls there, then we measure the superposition of both parts of the aerodynamic part of the pressure as well as the acoustic part. Yeah, concerning the advantages, I already have told some parts of it. Yeah, we really measure at the system at hand. We have a prototype, let's say, of a car, and we can put it in the aeroacoustic wind tunnel and do their measurements. Also, which are really advantages, that we have standardization towards measurements. Yeah, so there are standardization how to measure, for example, the radiated acoustic power and so on. So there is really standardization, which we do not have for numerical simulations. So this is still an open part we have towards numerical simulation. There are no standards, and you can believe or you cannot or you will not believe to the results. And a very important part is you can do long-term measurements. What do I mean with it? So for example, recording the signal of your microphones for about 60 seconds is no problem. So this is a standard and you record it, and then it's clear that you also get out smooth spectra because you can cut out of this long time overlapping time series to a Fourier transformation and average it, which is impossible more or less for simulations. Yeah, so when we look here for simulation, then for most problems, in order to really resolve the turbulence scales, you have a delta T, let's say, which is about 10 to the power of -5. So it's 10 microseconds. So, and you, as you know, you have to solve nonlinear partial differential equations with high sophisticated turbulence models. So that's impossible. So we are very happy to have, let's say, a simulation which is about 0.5 or okay, perhaps 1 second, but that already will take some weeks. Okay, what about disadvantages? Well, disadvantages clearly, it takes quite some time to install all the sensors. If you have clearly here a wind tunnel, well, you install them once. However, clearly other sensors which you apply, for example, to the surfaces, to the windows, for example, on a car, you always have to install it. But to give you just an idea, so one of the most sophisticated aeroacoustic wind tunnels is in Stuttgart. It's within Daimler company, and they have about 700 microphones mounted within their aeroacoustic wind tunnel, which are fixed in this sense and which, let's say, speaking, can look on the car when the wind is switched on, the flow is switched on, and you do then really with these microphones in a array structure, you can do with signal processing and get back where are the sources. But anyway, it's not only the costs, but also clearly the time you need for it. And you always need a prototype. So I would say this is the main part why it is so attractive, and the companies investigate quite some money in order to be able to already get an idea about your device at hand before you build the first prototype. Yeah, and then clearly a part which is also of interest is, all the physical quantities are not accessible. You cannot put everywhere a pressure sensor, and therefore you are quite restricted where you can do measurements, yeah, which is not the case for numerical simulations. So let's group them together. So when we look for acoustics, then it is clear the microphones are those sensors who are mostly used, and these microphones, as I have told you, are mainly installed in the acoustic far field out of the flow. You really have problems if microphones are within the flow. You can put some shieldings on the microphone, but anyway, mostly you have it outside the flow. And the same holds true for intensity probes. So if you have enough money, especially these MEMS these MEMS devices, as I've told you, from microflowne. So one sensor measuring all three components of the particle velocity and the pressure is about 20 kilo-euro. So you will not have so much intensity probes. So the standard is really for measuring the acoustic sound are microphones. Then towards the quantities for fluid dynamics, I would say the standard there we should start here is really pressure sensors, which you mount on different locations on the walls. And a second interesting sensor, a hot wire anemometry. This you can have. A standard is here again that you just have a measurement system for 1D, but there are also 3D systems on the market so that you are able to measure all three components of the velocity. Yeah, so this is for measuring the flow velocity and clearly the pressure sensors for the overall pressure, and you put them in the near field, especially where you have the flow. Yeah, and this is already high sophisticated to have a laser Doppler anemometry so that you are able to measure the flow velocity highly resolved in space and time. Yeah, for some special, let's say, experimental setups, more in labs, I would say you use LDA, but in practice, if you think here you are within a wind tunnel and you have the flow around the car, you will not use those. Okay, then towards aeroacoustic measurements, as I have told you, it is clearly important to have here a good acoustic environment with less reflections from the walls. So we have these aeroacoustic wind tunnels. Heavily used are there not only single microphones on discrete positions, but really a lot of microphones within a so-called array, and to beamforming. Beamforming is the name for the standard algorithm to compute back from your microphone signals where are the sources. And important here is also to apply correlation measurement, which means to correlate, for example, the signals you get out of the microphones which are at some distance of your car, for example, in a wind tunnel, and the wall pressure probes signals, so that you see in which regions of the frequency you have a high correlation, and then you can say, okay, there we have really this overlap, and these pressures I measure really contribute to the radiation of sound, which I measure with my microphones in the far field. So this is a technique used in a lot of different applications, but especially very powerful, and we will also see here some applications in aeroacoustics. Okay, so I think there will be no large questions. You have just heard from me some information in this sense, but we will go now in some details and looking at these sensors and looking at some environments of acoustic rooms. So important clearly are, and this is something which has to be, I would say, increase strongly in the near future, is that we have more, let's say, benchmark cases where we have very precise measurements with which we can validate our numerical simulation and perhaps also come up to some standards. As I have told you, that we really have measurement technology which are standardized, which are in norms, and this is clearly not the case for numerical simulations in this way. Typical applications, yeah, clearly transportation. As I already told you, in such wind tunnels, you not only can put there cars, so not only for car industry, for large size wind tunnels, you even can put a full plane in it, or um, um, rail, and a full rail train in this sense. Then clearly, which is strongly also coming up, are these parts of turbo, flow, and jet engines, and currently, very importantly, especially due to the fact we have a rising temperature, air conditioning systems, not only in cars, but just in your living rooms, for example. Yeah, and a problem coming up in the last years are clearly also wind turbines. They also make quite some noise, and this is also a specific, let's say, device where we have to investigate more in order to reduce the sound coming from wind turbines. Okay, so in this sense, just again showing our diagram concerning the frequency, the length scale, and the pressure amplitudes. We know towards the frequency we have a quite nice overlap between acoustics and the flow structures. Especially we have this vortex sound theory, and we have there can show that the shedding frequency, for example, of the vorticities being then generated is exactly the frequency you will also hear. So you have within your sound field. In the length scale, let's write down, we have this relation that the acoustic wavelength is approximately, or is proportional, let's say, to the characteristic length scale of a flow structure over the Mach number. So especially in the low Mach number region, there is a big discrepancy, and we should also consider this part here, that we are very often interested in what is the noise far away from any transportation system like airplanes, and then clearly this is a big disparity compared to the small scales you have within a flow. Yeah, and concerning the pressure, we also know that the hearing pressure, let's say the acoustic pressure, is quite small as compared to the pressures we have within flow. Just consider the ambient pressure, which is 10 to the power of 5 Pascal. Okay, the two fundamental experiments we will investigate, and we will show you measurement results and how they help us to understand the air acoustic phenomena, are first of it this square cylinder which is mounted here on this plate, and this is a typical structure we have here which generates tonal sound. And important here clearly for this part is what is the ratio of the height towards the diameter, which in our case, since it's a square cylinder, is the side length we have here. And as you see, it is not as high. Anyway, it's a factor of 6. We have moderate Reynolds number. Anyway, we kept the Reynolds number not too high in order to be also able to do numerical simulation and compare simulation with experiments. And it is clear as you look here to the flow that the cylinder reaches into the flow core. So the boundary layer here near the wall clearly is small compared to the height. So really the flow core hits our cylinder. On the other hand, we have this forward-facing step, as you can see along this picture here. Here we have a very small height in order to also have a realistic forward-facing step, which also happens within practice. So where you have small steps within your construction, for example, you see it here. So the height compared to our boundary layer is approximately 0.6. So the boundary layer will have a strong effect here on the physics we have there. We have also moderate Reynolds number here. The Reynolds number with the characteristic length scale taking the height of the step, and we call this our forward-facing step. So the flow is coming from here, and here it's going down the flow. And this is a typical example which generates broadband sound. And so these are two typical examples taken out once to investigate intonal sound generation. And we also had here a nice computation and comparison with these measurements, and the same for a typical example for broadband sound. Okay, one question. One of you already were in a aeroacoustic wind tunnel, somewhere in car industry or somewhere else?
For me, it was not specifically a wind tunnel, but an acoustic box.
Okay.
So they were not really working with the flow of the wind, but they had a lot of microphones around the cars and were investigating the engine noise, basically.
Okay.
Of like the standing car.
Okay. And it was in a company or somewhere at a company?
Yes, it was at BMW in Steyr.
Okay, yeah, clearly. Yeah, so the really aeroacoustic wind tunnel you have in Munich, that is also quite sophisticated, I would say, aeroacoustic wind tunnel for investigating their cars. Okay, yeah, so let's look at our possibilities that are actually possibilities we don't have here at the university. So this was our special, let's say, research aeroacoustic wind tunnel at the university in Erlangen, where it was actually just an acoustic room, and afterwards we installed all the devices to were able to have a possibility to investigate it, especially in these two fundamental ideas, this cylinder in cross flow and the forward-facing step. So as you can see here, main parts are clearly the ventilator, but importantly, clearly is here, this is here the part where we had our experiment set up and where the flow was coming out. And it is importantly, clearly, that the ventilator makes a lot of noise. So we had here special absorbers within the guiding pipes in order that the noise here you have without your setup compared to the setup makes really important difference because otherwise it is difficult clearly to get reliable measurements. So you see the possibilities we had with this very, very small, let's say, part where we could do the measurements, which is here, was in this case, we could generate here flows up to 50 meters per second. The volume rate was 2.7 cubic meter per second. We also had special guiding structures here in order to get a flow out, which has a low turbulence itself. So that was smaller than 0.22%. So we had a very homogeneous flow profile that was quite good. Anyway, as you can see here, at the highest flow velocity, without any obstacle in the measurement region, which is in this part here, was 72 decibels already aviated. Yeah, you know that at the low frequency you have a curve which cuts off more or less the sound pressure or reduce it strongly. So this was aviated. And when you compare it now with our anechoic room properties, you see we had a sound pressure level which was about 33 dB. And when you compare it really with the aviating, yeah, it was just 15 dB when there was nothing, let's say, on. Importantly, you see it was more or less a small room, 9 meter per 6 meter per 4 meter about, and the absorption coefficient we could reach here was quite nice, but if you look, that is the value larger than 0.9 is when we were looking at frequencies larger than 300 hertz. You know, at this low frequency, you have a large wavelength, and then you clearly need larger rooms as shown here. And that is really the room dimensions without the absorber you have at the walls in this sense. So we had all around absorbers, and the remaining space, let's say, of this room was this 9 meter per 6 meter per about 4 meters, where we have done quite a lot of measurements. And you see it is a room in room concept, and from this part here, so this gray part is a part of this anechoic room with these remaining dimensions. Here on the walls, clearly you had the absorbers, and as you know, they have to be thicker and thicker the lower the frequency is. And you see that this outer part we clearly put out, where we have the ventilator and this closing for the flow we had out of the anechoic room. And this is also a standard, this room-in-room concept for most setups. Here a little bit investigation what we have also developed by ourselves. So this is here, especially on this picture, you see our microphone array. So all the microphones are positioned on this plate here. And you also can see here the nozzle where the flow is coming out. And actually what you see here was this basic experiment with the forward facing step. So here you can hopefully see a little bit the step we had here. So there were 2 plates mounted on each other. And that was here just a compressor where you then can see such a source map in this sense, where with all the recorded microphone sensors, we applied the beamforming technique, and then you can project more or less your source map on the geometry of your device. So as you can see here, we had 64 channels, 64 microphones, a sampling rate of 48 kilohertz, and 24-bit analog digital conversion. We used electret microphones, which you get quite cheap. So not really the high standard from Brüel+Kjær. Anyway, all the microphones were calibrated, which is very importantly, especially the phase is important to have a very precise calibration, as you know, because the traveling distance makes you the phase in the signal, and so you need there a high accuracy. So if you have such microphones, you have to calibrate them, and the calibration was clearly done with high sophisticated capacitor microphones from Brillium Care. Yeah, importantly is that you have a pre-amplifier, as you see here a little bit. Yeah, there is some length of the cable until you reach then your recording system. The recording system was also outside the room. That's a standard that all these devices you don't need within the room. You have outside the room so that you can steer it from outside all your measurements. And so you need here pre-amplifiers directly at the position of the microphones and already filter out their noises. So we also have developed our own signal processing software for this microphone array. This is, as I told you, where you compute back from the recorded signals where the sources are located. And this, as you can see, we have different configurations we can do. In this case, you see that the microphones are positioned really on a ring, and you have here the microphones on the outer ring and on the inner ring in order to have here better distributions and get a better resolution at the end of your source map. Okay, so let's also go a little bit towards this correlation measurement technology. What we mean with it, it is exactly what I told you. What makes sense is here really to have microphones at some distance outside the flow, and on the other hand to have wall-mounted pressure sensors here directly on the wall of the cylinder. You see here this sketch which nicely fits to our experimental setup in this anechoic room. We have here the nozzle where the flow is coming out. This is the base plate, and we have here the mounted cylinder as an obstacle, and we directly positioned pressure sensors on the cylinder itself and microphones at different distance. And the interesting point is here the coherence itself. And as you can see here, this coherence spectra already in the frequency domain is that you compute the cross correlation spectra and normalize this to the autocorrelation spectra of the X signal itself and the Y signal. So let's say the X signal is our wall-mounted pressure probe, and the Y signal we get from our microphone at some distance outside. And so we really can correlate the pressure directly within the flow, which is clearly mainly dominated by the aerodynamic pressure, but superposed also the acoustic pressure. And we really get the acoustic pressure here with the microphone at some distance where there is no flow. And so it helps us to see which part clearly, because that is obtained by performing a cross correlation, which part you have seen here by within the signal of your wall-mounted pressure also within the microphone. And so you see what you then at the end really compute when you have this coherence function gamma, that you take your signal and multiply this signal here with this coherence function to get rid of additional noise you have and generation mechanisms you measure with the wall mounted pressure sensor, which are not really radiated, because what is radiated clearly you measure with the microphone. And if you have here a comparison. So the blue line you can see here is without the cylinder itself. So you just have the base plate here, the flow is coming out, and you see this is the spectra in blue, what you measure here with the microphone. On the other hand, when you then have the cylinder as an obstacle within the flow, and you directly use the signal of the microphone to a Fourier transformation, then you get here this red signal. You nicely see here that you have at this frequency a strong increase over this, let's say, blue base signal. You also see here some peak, which is actually really the second or first harmonic of the base frequency here. However, if you do this correlation approach we have here and shown in this formula here, so you have this coherence function, multiply this with your autocorrelation function of the microphone signal, then you get this nicely green spectrum here, where we now really see that we have here this strong increase, and here it is then clearly this is due to aeroacoustic phenomena, as we know that when the flow is coming from here, you have here at this surface and the opposite surface, you have the shedding of the vertical structures, and you have here downstream direction the von Karman street. And it is also nicely clearly shown here in blue. You know that you have this kind of dipole radiation structure, so it makes sense to position the microphone exactly here at this position outside. However, we also have additional noise generated, also flow-induced noise, but which we are not interested because we want to investigate what is the generated sound, flow-induced sound due to our obstacle, which is clearly directly from the flow coming out of the nozzle. And we should not forget that clearly also the flow here along the plate, that here at the end of the plate, clearly you will also generate here some turbulent structures, and they will also generate clearly here a sound field, and all this you record with your microphone. So you see, that makes sense to use this correlation technique as shown here in this part. Yeah, important here is also, but I think some of you already know it, that when you compute the spectrum of a signal, and that is now the same, if we really here compute the correlation of two signals in the frequency domain, that as you see here, if you have here your signal, that you really cut out a lot of overlapping time series. And for each of these time series, as you can show here, you do a Fourier transformation, you compute here the cross correlation. You know, the cross correlation, if you transform this in the frequency domain, it's the spectrum multiplied with the conjugate spectrum of the second signal. And you see you have this sum here, normalized by the number of blocks you take out from your long time signal, and you here a Hamming window has been used with 50% overlap. This you see is the Hamming window, so that you get smoothly to 0 at the beginning and the end of each block. And for this Hamming window, this is the correction factor. Fs is the sampling frequency, and with this you get then your averaged cross correlation spectra in this sense. And with this average cross correlation spectra, as well as autocorrelation spectra of each signal, you then also compute your averaged coherence spectrum you get. Therefore, we have this gamma XY and we have this additional bar on it. So that's the standard, and that clearly you can do when you think you have a measurement time of, let's say, 30 to 60 seconds. Then you can make here blocks, let's say up to 50 blocks, and you get here a really good approach in order to average out additional noise which is coming from elsewhere and which is not really within the physics we want to measure. Yeah, an important thing is also what you should do and correct is the different runtime. And as you know, we do the correlation here between the pressure probe mounted here on this wall of the cylinder and the microphone. But we also know we have the retarded time. So it takes some time when waves are generated here until they approach the microphone. And exactly this flight of time you have to correct in order to really correlate, to get a correct correlation between the two signals. So in this sense, this correction has to be done in this way. And you see it also here, the estimated error you can compute here is exactly this factor here you have, where tau 0 is the runtime of the waves being generated here at the position of the cylinder and the need in order to come up here to the microphone. Yeah? So that means you can look here how large your error is. Anyway, especially in real wind tunnels, the microphones have really some distance, which is, let's say, between 10 and 30 meters or even more. And then you should correct your signal. Let's say here the X signal is the signal coming from the microphone. Then you should correct here this by the time shift before you compute the spectra and especially compute the correlation as shown here. Okay, so today what we will focus on or start at least, will be the cylinder in cross section, which is, I would say, experiment already being investigated heavily in the literature, especially in the research literature. We know a lot of it, and especially we know also, let's say, the switching on of the von Karman street. So if you have a Reynolds number larger than 60 about, which is quite low anyway, but you will have this generation of vortical structure at the shedding frequency, and you get the von Karman vortex street. We already also have discussed about the Struhel number that is computed by the shedding frequency, the characteristic length scale. For the characteristic length scale, you take here the diameter of the cylinder and a characteristic flow velocity, and here you take the flow velocity of the inflow. Yeah, and what you see here on this picture, a nice picture, is here that this a picture which shows you here the flow and the vortical structures here, the so-called von Karman street, and that has been visualized by smoke. Yeah, so you bring in some smoke, and the smoke particles then are affected by the flow, and you get such a nice spectrum. So this is our setup. The shedding frequency we have here was about 50 Hertz. The Struhel number of our setup is about 0.1, so 0.1. And what you see, what have we investigated here in the first measurement campaign was that along this measurement plane we have moved our hot wire probe, and you can see here the standard deviation of the velocity. So really the fluctuating part of the velocity, and you nicely see that this starts here and goes downstream, and at this position here we also did a Fourier transformation of the recorded signals. And nicely what you see here in the spectrum, so it's the spectrum of the measured flow velocity here, is that you have this strong peak at this position, which is nearly by 50 Hertz. And this is exactly the shedding frequency. So you can see this very nicely already in the measurements of your flow velocity, which has been done, as you can see here, by a hot wire probe. Now, if we go on and evaluate our microphone measurements, as you can see here, that is about the distance that was about 1 meter distance, and we had on both sides a microphone, and then clearly moved also the microphones in order to get the directivity pattern, which is shown here. But first of all, let's look at the spectrum here of one of the microphones, and please look here. We have here in green one the obtained spectrum of the microphone for a inflow velocity of 10 meters per second, and in red the inflow of 30 meters per second. And in both cases you also see the spectrum recorded, computed from the recorded microphone signals when you just have the base plate. So this is here in black. So we see at this position here in green, really when there is the cylinder mounted on the base plate, and you see here in black the recorded signal and then computed spectrum when you just have the base plate. Nicely, what we see here also when we increase the velocity from 10 meters per second to 30 meters per second, where the flow is more or less a turbulent flow now for our configuration, then you see here the red line, which is the spectrum of the recorded microphone signal with the cylinder, and in blue it is here without the cylinder. What we nicely see that the value of the sound pressure level here increases in the amplitude, and nicely what we also see here is the shift of the shedding frequency here from about 50 Hertz to about 150 Hertz. And that nicely correlates, as you can see here, with the flow velocities. And as you know that for a large regime, the Strouhal number is more or less the same. And we know that the shedding frequency is then a function of the velocity, and it increases clearly with the velocity. And we see also that this factor of 3 we have in the velocity is directly also about the factor of 3 in the shedding frequency. And in addition, also the higher the velocity, inflow velocity, the higher we also have here the sound pressure level. Okay, and yeah, as we know, we also have some increase in the sound pressure level at the higher harmonics, especially at double the shedding frequency. But looking at our spectra, you see that we could not really resolve this part. On the other hand, if you move your microphones in this sense, you see here and record always the signals and the computer spectra and normalize here the intensity. That what you see here would be an exact dipole. Yeah, we did it just on one side here, and you see what we got out is somehow like a dipole radiation. That was here done for the case where we had 30 meters per second. And exactly that was done here for a third octave with one at about 160 hertz. So you see here there is some deviation. Clearly, is not the optimal one, but at least this radiation pattern is like we see here a dipole, and please have in mind that is a dipole without the effect of a flow. When there is a flow in this sense, then we have more or less a dipole which is going towards the upstream direction. So what is shown here with this arrow here is this is the flow direction, and so you see that the radiation here is going upstream compared to an idle dipole you generate, let's say, for example, with two loudspeakers. So you have a radiation without effects of the flow. So this is an additional thing, and that you see especially also by high velocities in this sense that the radiation pattern is always inclined towards the upstream direction. We see nicely the effect of the flow velocity to the shedding frequency, which is also the frequency, the main frequency we hear. And you also see the impact that the higher the velocity, the higher the generated sound. So this is what we can get out, and nicely, as you can see, it also compares with what we know from theory, and clearly also what we get out from numerical simulations. Do you have any questions here concerning this setup, let's say, and the first evaluation of our sensor signals here with the hot wire probe, and here the investigations we done by the recorded microphone signals?
Yeah.
Yeah.
How would it be with 30 meters per second with a laminar flow, so not turbulent?
As you know, it's a function clearly of the velocity and your length scale parameter. So if you change the dimensions of your cylinder, you still could have also a laminar flow for the cylinder itself, yeah, at 30 meters per second. For our case, I think this is missing. So has Stefan not put in, I guess, the dimensions? Where are our? Yeah, okay. Yeah, exactly. That's good. We just have the ratio. Sorry. I have to look up. That was mainly done in a PhD thesis by Christian Hahn at the time when I was in Erlangen. I will provide for you the absolute values of the height and the I think that the side length, I'm not fully sure, but I think the side length was just 2 centimeters. So you see the height was 12 centimeters. But, and yeah, I will provide, that makes sense. Yeah, so that you have
So
a more impression how large our obstacles were. Yeah,
so we would need a larger
exactly,
obstacle
exactly.
in terms of getting a laminar
Yeah,
flow
exactly,
with
exactly.
the same
Yeah,
speed.
yeah.
Okay.
But as
And
you
if we
see,
change the Reynolds number,
yeah, clearly you change then the
yeah,
Reynolds number when you have a larger diameter, because the
yeah,
diameter
sure.
was used here to evaluate the Reynolds number.
Mhm.
And this is, let's say, it is also, it is clearly a very basic experiment, but we did quite some cooperations in this case with Audi, and there it was clearly for the side mirror. So you can also see this as a simple setup of a side mirror. But as you see here, we also scaled our obstacle in such a sense that we could do measurements in this very small aeroacoustic wind tunnel, if whenever you can name it a aeroacoustic wind tunnel, because it was just a anechoic chamber, and some years later we were starting with aeroacoustics and doing experiments. So it is, yeah, we had a lot of restrictions there.
Mhm. Okay, thank
Okay,
you.
I will look up so that we get also the absolute values of the dimensions. But as I remember, the side length was here 2 centimeters, so the height in this sense was then 12 centimeters.
I did a little calculation. So for 10 meters per hour per second, it's 2 centimeters.
Yeah,
But,
okay.
yeah.
Okay, okay, yeah. Anyway, I will look up so that we have the correct values, and I'm not really sure now about the height of this forward-facing step. I think it was 0.5 centimeter or something, so 5 millimeters, but I will look up and provide it to you for the next time. Okay, further questions or comments?
Yes, I have a
Yeah.
question about the pressure sensors you mentioned
Yes.
some slides ago. Because you have some pressure sensors on the surface and
Yes.
then microphones away. So what kind of pressure sensors?
Yeah, that yes. If you want to, it's Coolite. Very expensive pressure sensors. Also, what I should mention, so these Coolite are piezoresistive sensors. I don't know if you know piezoresistive sensors, so they change their ohmic resistance via a pressure. If you apply a mechanical pressure, or in this case a flow pressure, on this on the active area of the sensor, then they change actively the ohmic resistance, and it is then the first signal processing is done by a Wheatstone bridge, and the diagonal voltage you get out is then clearly amplified. Do you know this part?
No, not really.
Okay, I will show you, at least if you don't know it. So this Wheatstone bridge is as follows. So you provide here with a voltage, and what you have here, let's say, are fixed resistors with the same value, and here is your sensor. Yeah, and the sensor, as I have told you, this microphone, these Coolite sensors, they have the piezoresistive effect. So by the fluid pressure, they change the resistivity.
Mm-hmm.
And you get then, so you see out of the change of a resistivity, you get the change of this voltage here. Yeah.
Yeah.
And this voltage then clearly is going into a preamplifier, and then you have filters and whatever you have there.
Mm-hmm.
Yeah. But that is the main signal processing of this sensor, and the sensor itself is piezoresistive. Yeah. You could also, there are also some piezoelectric sensors on the market, but these special sensors piezoresistive. And what I should also tell you, I guess I have not told you, it has to be flash mounted. Yeah, very sensitive here. Yeah, so the sensor you don't put on the wall. Yeah, so you have to make a hole on the cylinder, put it in, and so that the surface, the active surface of the sensor is flash mounted, so that you not really also have an effect due to the mounting of the sensor on the flow. That would be not good. So it has to really be flash mounted on the surface.
Okay, thank you.
Yeah, very good question. So I've missed this very important information clearly in practice. So if you would have there just the mounting of the sensor, it would be also like a small step you have there for the flow, and that clearly would affect your experimental setup and something what you don't want to have. That will additional generate some turbulence structures there, and therefore also some additional sound which we don't want to have. Therefore, this flash mounting is very important. Okay, any further question or comments?